Hello friends, I welcome you in lecture number 5 on heat equation. In this lecture also we will discuss one more question on heat equation which was asked in GTU Summer 2020 exam. Here also we are going to consider the case of heat equation in which boundary conditions are in such a way that temperature is 0 at both the ends of the given metal rod or given metal bar. But here initial condition is not given directly. We have to determine the initial condition from the description of the question, and before that we have to understand two states of the system which are known as steady state system and unsteady state system. So what is meaning of steady state and unsteady state? So we are familiar that one dimensional heat equation is given by del U by del T equal to C square times del square U by del X square, and here U is the temperature which depends on the position X and time T. Now in some situations it is given that temperature U does not depend on time or U does not vary with time. So in that case U is a function of only one variable X. So that type of state is called steady state of the given system. So steady state situation, that means the temperature is independent of time T, and in that case this partial derivative of temperature with respect to time T is 0, and we always have U as a function of only one space variable X in one dimensional case. In unsteady state U depends on the time T. So whatever questions we have discussed so far, in all those questions we are considering U as a function of both the variables X and T. So we have taken in consideration unsteady state so far. The questions which we have discussed on heat equation in earlier lectures, in all those questions we have taken unsteady state situation. Now sometimes you are not given the initial condition for unsteady state, but you are given the steady state condition. So using that steady state of the system, you have to first decide that what is the initial condition for given problem, and then you will be able to decide the solution of unsteady state problem. So here we have mixture of both the states. So I have given title as steady state condition. Initial condition will be decided from the steady state situation. So we understand with the help of this example. What is given? A rod of 30 cm long has its ends denoted by capital A and B kept at 20 degrees Celsius and 80 degrees Celsius respectively until steady state conditions prevail. So this is the situation in steady state system. So during this situation, during this steady state, temperature U depends only on one variable, say position, or U is a function of X only. And during this steady state of this system, it is given that temperature at end A is 20 degrees Celsius and temperature at point B is 80 degrees Celsius. And U does not depend on time, U depends on X only. That means partial derivative of U with respect to T is 0 during this steady state situation. So first we have to decide that in steady state situation what is the solution of the system. So first we consider this steady state situation of the system, and they have given that value of temperature during this steady state is 20 degrees Celsius at first endpoint and 80 degrees Celsius at second endpoint until steady state conditions prevail, and length of the metal bar is given as 30 centimeter. That means value of L is 30 centimeter. So first I will decide that during steady state situation what is the solution of the system, and we know that in steady state situation u depends only on one variable, say x. So we have to decide what is the solution of the system during steady state situation. Now as I discussed that if we have this temperature distribution problem, then it is governed by one dimensional heat equation, del U by del T equal to C square times del square U by del X square. And if we are in steady state situation, then del U by del T is 0. Therefore we have 0 equal to C square times del square U by del X square. Now we know that this C is a positive constant, therefore C square is also positive, and we must have del square U by del X square equal to 0. Now during steady state we know that U is function of X only, so this I can write as d square U by dx square equal to 0. So it is second order linear ordinary differential equation which is homogeneous, and to solve this we have to write down the auxiliary equation. So auxiliary equation for this is, say, m square equal to 0. Therefore we have m equal to 0 repeated and real roots, and we know that if we have real and repeated roots, then general solution is u equal to a times e raised to m into x, value of m is 0, plus b times e raised to m into x, m is again 0, so I have to multiply this by x, and therefore u equal to a plus b times x, because e raised to 0 x is 1. So we can see that solution is u equal to a plus bx, which is function of x only, and this a and b are arbitrary constants. Now we can use this fact that until steady state conditions prevail, temperature at point A is 20 degrees Celsius and temperature at point B is 80 degrees Celsius. Now suppose we consider this along the x-axis. Suppose this is taken, rod is taken along x-axis, then this end is at x equal to 0, and because length of the rod is 30, at this end value of x is 30. So we can say that when x equal to 0, value of u is 20, and when x equal to 30, value of u is 80. So we have two boundary conditions, and using those two boundary conditions we can obtain value of a and b. One boundary condition is u0 equal to 20, and another boundary condition is u of 30 is 80. It is given that until steady state conditions prevail, temperature at endpoints is 20 and 80 degree respectively, so that we are using here. So if I take u equal to 20 and x equal to 0 here, I will obtain a equal to 20, and for this I am taking u equal to 80 in this equation and x equal to 30. So I will write a plus b into 30 or 30 times b. Now what is a? A is 20, so that we substitute here, plus 30 times b. Therefore 30 times b equal to 80 minus 20, that is 60. Therefore b equal to 2. And once we obtain a and b, we substitute them here. So A is 20 and B is 2. So I will have during steady state situation the function u is 2x plus 20. So this is the solution of the heat equation in steady state situation. So we can say that value of u is 2x plus 20 at initial time, say t equal to 0. We will consider ux0 equal to 2x plus 20 for every x between 0 and length of the bar, which is 30. So using this information, that what is the temperature at endpoints until steady state conditions prevail, we can determine the initial condition which we will use to find out the solution of heat equation during unsteady state situation. So far I have used only first part, that rod of 30 cm long has its ends A and B kept at 20 and 80 degrees Celsius respectively until steady state conditions prevail. So using this portion, I am able to decide my initial condition ux0, which I have obtained as 20 plus 2x, and this condition satisfies these two boundary conditions. Suppose I take x equal to 0 here, then I will obtain u equal to 20. If I take x equal to 30, then I will have 20 plus 2 into 30, that is 60, and 60 plus 20 is 80. So this is the situation before the case that unsteady state situation starts. So this is at time t equal to 0, and that is our initial condition. Now after time t equal to 0, it is given that temperature at each point at each end is suddenly reduced to 0 degrees Celsius. So after time t equal to 0, temperature is reduced to 0 degrees Celsius at both the endpoints. That means they are considering u0t equal to 0, and the value of temperature at 30 is also 0. The temperature at each end is suddenly reduced to 0 and kept so. That means it will remain same for all time, which is positive. Now they are considering that temperature is reduced to 0 at endpoints, and this is for all time t greater than 0, and find the resulting temperature from the end A. So suppose I am interested in the value of temperature at this point, then I have to find out from the end A. So what is the temperature at this point from this end A during unsteady state situation? So now we have to solve the heat equation del u by del t equal to c square times del square u by del x square, in which we have boundary conditions are that temperature is 0 at both the ends, and initial condition is ux0 equal to 2x plus 20. And to solve this type of problem, we have ready-made formula. We know that the solution is given by sigma bn times sin n pi x by L e raised to minus lambda n square t, n equal to 1 to infinity, where bn and lambda n are having their formulas. Lambda n is cn pi over L, bn is given by 2 by L integral from 0 to L fx sin n pi x by L integral with respect to x. And we have solved this type of problems in previous lectures. In lecture number 3 and 4, we have seen how to solve this type of problems. All we have to do is we have to calculate value of Bn and lambda n and substitute in this standard formula, which is applicable when temperature is 0 at both the ends and ux0 is fx, which we will use to find out Bn. The situation which is new is here initial condition is not given directly, but they have given that during steady state what is the temperature at the end points, and using that information that during steady state we must have del square u by del x square equal to 0, and using that information we obtain the solution during steady state situation, and using this information, temperature information at end points during steady state, we are able to decide the initial condition, which is u equal to 2x plus 20 in this problem. So we have to write systematically. Here I have written all these things which I just discussed, that the equation for conduction of heat is given by this, and here I have written that prior to the temperature change at the end points A and B, the heat flow was independent of time, that is steady state condition for which del u by del t is 0. Therefore equation 1 becomes, that is in this equation I take del u by del t equal to 0, and as I discussed I have solved this, and u is a plus bx. Now it is given that ends A and B of the rod are kept at 20 degree Celsius and 80 degree Celsius respectively until steady state conditions prevail, that is when x equal to 0 at point A, u is 20, and when x equal to 30, that is at end point B, value of u remains 80 until steady state conditions prevail, that is during steady state situation the boundaries are at temperature 20 and 80, and using these two boundary conditions we have obtained values of A and B, which I just discussed. So finally I find that initial condition is expressed by ux0 equal to 2x plus 20, and they have given the boundary conditions for unsteady state are that temperature is 0 at both the ends. The length of the metal rod or metal bar is 30, so at this point x is 30 and at this point x is 0, and they have given that after temperature change they are considering temperature as 0 at both the endpoints. And now we know that the solution of this problem in unsteady state is given by this formula, and now we find out lambda n in Bn. Here we mention that value of L is 30, that is length of the bar. Lambda n is given by C n pi over L, C n pi over 30, n takes the values 1, 2, 3 and so on. And what I have to calculate is, now I have to calculate Bn. Bn is given by 2 by L integral from 0 to L fx times sin n pi x over L integral with respect to x. Fx is given by initial condition, value of L is 30, so let me take L equal to 30 here. Here also I am writing 30. Fx is given by initial condition, that is temperature at time t equal to 0, which is 2x plus 20. So here I am writing 2x plus 20, and in sin n pi x by L I write L equal to 30 integral with respect to x. From this I can take 2 common, and that 2 I can take outside the integral, and this 2 by 30 means 1 by 15 into 2, and let me write this as, here I take 2 common, so I am left with x plus 10 sine of n pi x divided by 30 integral with respect to x. This is equal to 2 divided by 15, and now I apply integration by parts here. I consider u equal to x plus 10, v equal to sine n pi x by 30. So u as it is, that is x plus 10 as it is. Integral of sine n pi x by 30 is minus cos n pi x by 30 divided by n pi over 30, that I rewrite as 30 over n pi in the numerator, and cos n pi x over 30 minus derivative of x plus 10, which is 1, and integral of this whole bracket. So again I have to divide by n pi by 30, that is square of 30 over n pi, which is 900 divided by n square pi square, and here integral of cos is sine function sine of n pi x over 30. Limits of x are from 0 to 30. Now I am taking directly, first I take x equal to 30 for upper limit, and let's see what we obtain. So here if I take x equal to 30, here I will have 30 plus 10, that is 40, and I already have one negative sign, so this I write as 40 into 30 divided by n pi. If I take x equal to 30 here, this 30 will get cancelled and I will have cosine of n pi. Here if I take x equal to 30, I will have sin n pi, and n is positive integer, therefore sin n pi is 0, and therefore this whole term becomes 0. Minus, I have to take lower limit x equal to 0. So here I will have cos 0, that is 1. If I take x equal to 0 here, I will have 10 and into minus 30 divided by n pi, and there is 1 minus from lower limit, so that I consider as negative negative positive, and what I am left with 10 into 30 divided by n pi, let me write cos 0, and this is going to be 0 because sin 0 is 0. Now here we can see that 30 over n pi we can take common, so let me take 30 over n pi outside the bracket. Here cos 0 is 1, and here I am left with 10 minus, here I have 40, and cos n pi I can write as minus 1 raised to n. I have taken 30 over n pi common, here I am left with 10, here negative sign, and here I am left with 40 into cos n pi. Cos n pi is minus 1 to the power n. We can take this 10 also common, and here I cancel this 15. So I have 4 divided by n pi. Again I am taking 10 common, and here I have 1 minus 4 times minus 1 raised to n. So finally we have this expression for coefficients Bn, 4 into 10, that is 40 divided by n pi, and this is 1 minus 4 times minus 1 to the power n. N takes the values 1, 2, 3 and so on. So once we obtain Bn, and then we can write down the solution simply by substituting value of Bn. Uxt is given by sigma n equal to 1 to infinity Bn sin n pi x over L. L is 30 here, e raised to minus lambda n square times t. and Bn is given by this 40 over n pi 1 minus 4 into minus 1 raised to n. Now this 40 over pi is independent of n, so that I directly write outside the summation. 40 over pi sigma n equal to 1 to infinity, and here 1 minus 4 times minus 1 raised to n divided by n sine of n pi x over 30. Lambda n was cn pi over 30 and square of it. Lambda n is cn pi over L, L is 30. So I can write one more step. This is 40 over pi sigma n equal to 1 to infinity 1 minus 4 into minus 1 raised to n divided by n sine of n pi x divided by 30 e raised to minus c square n square pi square t divided by square of 30, that is 900. This is the required solution, or the temperature at any point x and at any point t. We are asked to find out the temperature at any point x comma t from this and a, and it is given by this formula. So this is slightly different question. Here we are not given initial condition directly, but we are given that during steady state situation what is our system, or we are given that during steady state situation temperature is given at both the ends. So using that information and using the heat equation, that during steady state heat equation becomes del square U by del x square equal to 0, and this is the solution of heat equation during steady state situation. And using the information that temperature at end points is 20 and 80, we are able to determine these constants a and b, and whatever we obtain, that is the initial condition. This is the situation at time t equal to 0, and after this they are considering the change in temperature. So they are considering that temperature at both the ends is reduced to 0 degree Celsius. Therefore during unsteady state situation boundary conditions becomes temperature 0 at both the end points, and using these two boundary conditions and this initial condition we are able to determine the temperature at any point x and at any point t on the metal bar. So this is very nice question, and it was asked in GTU exam single time. Generally they are not asking this type of questions, but it was asked in GTU Summer 2020 exam. But it is easy, you have to just remember that during steady state situation del u by del t equal to 0. So solve this equation and find out your initial condition, and once you obtain initial condition we have ready-made formula for the solution of heat equation with this type of boundary conditions. So this is all about this session. I hope you like it. Thanks for